Welcome to Topic 7, Deep Learning Basics for Marketing and Natural Language Processing. My name is Sujin Han at Mavalab. Today, we move from classical text models into the core workflow of neural networks. Think of this lecture as the bridge between the methods you already know and the transformer models we will study next week. By the end of this notebook, I want you to do more than recognize deep learning vocabulary. You should be able to explain what layers and activations do, build a simple neural text classifier, read learning curves, diagnose overfitting, and use regularization tools such as dropout, L2 regularization, and early stopping. You should also understand why embeddings inside deep models are learned for the task itself, and how this workflow carries over to transformer fine-tuning next week. Modern marketing is full of text. We see it in reviews, social posts, survey comments, chat logs, service notes, and product descriptions. Classical methods such as term frequency, inverse document frequency, topic models, and word-to-vec are still strong baselines. Deep learning becomes valuable when we need richer representations, better handling of complex language patterns, or end-to-end learning where the model can discover useful features by itself. The trade-off is that deep learning usually needs more data, more compute, and more operational care. Our plan today is straightforward. We will set up the environment, define where deep learning fits relative to a baseline, review layers and activation functions, convert text into token IDs and embeddings, train a simple model, diagnose overfitting, apply regularization, inspect learned embeddings, and then connect everything to the transformer workflow. So this is not just a coding exercise. It is a full modeling workflow from data to business decision. This cell reminds us that today is not isolated. Earlier weeks covered pre-processing, sparse text features, sentiment classification, topic modeling, perceptual maps, and product embeddings. Today unifies many of those ideas under one training loop. We will still represent text, learn similarity, and evaluate model quality, but now the representations are learned automatically. Next week, the same training logic stays in place while the representation becomes contextual and the main architecture becomes attention-based. This code cell handles setup. We fix the random seed once so our results are as reproducible as possible, import the libraries we need, and check the TensorFlow version and whether a GPU is available. The output tells us we are running TensorFlow version 2.19 and that a GPU is available. That matters because deep learning training can be slow without hardware acceleration, even though this notebook uses a relatively lightweight model. Before the main analysis, the notebook introduces a few helper tools. This is a small organizational step that keeps later sections easier to read. The important idea is that we want reusable functions for plotting learning curves and checking basic text properties so that our attention stays on modeling decisions rather than repetitive code. This cell defines helper functions. One function plots training and validation curves so we can judge whether the model is learning or overfitting. Another summarizes text length, which helps us think about sequence length later. There is also a simple sigmoid function for demonstrations. I would not spend much class time on the syntax here. The key point is that good notebooks separate utility code from the main modeling story. To keep continuity with the earlier sentiment module, we use a practical binary classification task. The goal is to predict whether a Yelp review is negative or positive. Binary classification means there are only two labels. This is marketing relevant because companies often want a fast signal for review monitoring, service quality tracking, or brand health dashboards. We deliberately sample a balanced subset, so the metrics are easier to interpret, and the notebook runs quickly enough for teaching. This code streams the Yelp polarity dataset, shuffles it, and collects an equal number of negative and positive reviews. Streaming means we do not have to load the entire dataset into memory at once. The function also normalizes white space and skips empty text. In the output, we see 5,000 total reviews, with 2,500 from each class, plus a few example rows. That gives us a balanced teaching dataset that is large enough to show real behavior, but small enough to train quickly. Here we do a quick sanity check. The class counts confirm a perfect 50-50 balance, which means accuracy will be easy to interpret. We also look at text length. The median review length is 528 characters, the mean is about 709, and the longest reviews are much longer. That tells us customer text varies widely in length. In practice, any fixed sequence length will keep some reviews in full and truncate some long ones, which is an important design choice in deep learning. This markdown cell reviews the split discipline. Training data is where the model learns its parameters. Validation data helps us tune settings and decide when to stop training. Test data stays hidden until the end, so we get an honest estimate of future performance. Using the same split for both the baseline and the deep model makes the comparison fair. Otherwise, differences in data partitions could look like model improvement when they are really just sampling noise. This code performs a stratified split, which means each partition keeps the same class balance as the original data. The result is 3,500 training reviews, 750 validation reviews, and 750 test reviews. Each set remains perfectly balanced across positive and negative labels. That matters because we want performance differences to reflect model quality, not accidental class imbalance. It also mirrors a clean production workflow where tuning decisions are separated from final evaluation. Before touching a neural network, we build a strong classical baseline. This is good science and good business. If a simple method is already strong, then a more complex model has to justify its extra cost. The baseline here uses term frequency inverse document frequency features and logistic regression. That combination is a classic workhorse in text analytics because it is fast, stable, and often surprisingly competitive on sentiment tasks. The code turns training reviews into word and bigram features, then fits a logistic regression classifier. A bigram is a two-word sequence, which helps capture phrases such as very good or not worth. On the validation set, the baseline reaches accuracy of 0.84, F1 of 0.842, and area under the curve of 0.935. F1 balances precision and recall, while area under the curve measures how well the model ranks. Positives above, negatives across thresholds. These are strong numbers, so the deep model will need to earn its place. This short cell simply reminds us to keep the baseline results for later comparison. That is important because deep learning should not be judged in isolation. A model is only better if it improves on a meaningful benchmark under the same evaluation setup. Now we move into the conceptual core of neural networks. A layer is a learnable transformation from one vector space to another. A dense layer takes an input vector, multiplies it by weights, adds a bias term, and produces a new vector. But if we only stack linear layers, the whole network is still just one big linear transformation. That is why we need an activation function. An activation introduces non-linearity, which lets the model learn richer patterns. For example, a linear model might miss interactions such as a word becoming negative only when another nearby word changes its meaning. This is also where we connect back to logistic regression. Logistic regression is already a tiny neural network. It is basically one dense layer followed by a sigmoid that converts the score into a probability. This cell prepares us to visualize three common activation functions. Sigmoid squashes values into the range between 0 and 1. Hyperbolic tangent, or TANH, squashes values between -1 and 1 and is centered at 0. Rectified linear unit, or ReLU, outputs 0 for negative inputs and keeps positive inputs unchanged. Each choice changes how information flows through the network and how easy the model is to train. The code draws the sigmoid, ton, and ReLU curves. When you look at the figure, notice that sigmoid and ton flatten at the extremes, which means gradients become small there. ReLU does not saturate on the positive side, which is one reason it became so popular in deep learning. The broader lesson is that activation functions are not cosmetic. They determine how flexible the model can be and how smoothly it learns. This cell states the main takeaway clearly. Without activation functions, a deep network collapses into something that is not meaningfully deeper than one linear layer. So when we say deep learning, the word deep only matters because nonlinearity lets the layers combine into something more expressive. Deep models cannot consume raw text directly. They need tensors, which are structured arrays of numbers. Earlier in the course, we converted text into sparse vectors using term frequency inverse document frequency. Sparse means very high-dimensional with many zeros. Deep learning usually prefers dense representations. First, we map each token to an integer ID. Then we map each ID to a short dense vector called an embedding. A token ID is just a lookup key. The embedding is where the semantic learning happens. This two-step pattern will remain important when we move to transformers. For this notebook, we use the Keras text vectorization layer as a simple tokenizer. Tokenization means breaking text into smaller units, usually words or subwords, that the model can process. This layer learns a vocabulary from the training corpus and converts each review into a fixed-length sequence of token IDs. It is simple enough for teaching, while still showing the same basic workflow used in larger models. This code creates the vectorizer with a vocabulary cap of 20,000 tokens and a sequence length of 200. It lowercases text, removes punctuation, splits on whitespace, and, most importantly, adapts only on the training data to avoid leakage. The output confirms a vocabulary of 20,000 tokens and shows the first few reserved and common entries, followed by token IDs for one example review. Conceptually, the review has now been turned into a sequence of integers. That is the bridge from language into something a neural network can learn from. This is a subtle but important detail. Token ID 0 is usually reserved for padding, which fills unused positions when a review is shorter than the fixed sequence length. Token ID 1 is usually the unknown token used for words outside the vocabulary. Later, when we inspect embeddings, these reserved IDs matter because they occupy real rows in the embedding matrix. So the mapping from token to vector is not arbitrary bookkeeping. It affects how we interpret learned parameters. Here is the first complete deep learning architecture in the notebook. The flow is simple. Raw text goes into the vectorizer. Token IDs go into the embedding layer. The sequence of word vectors is reduced to one document vector through global average pooling, and then a small dense network predicts positive or negative sentiment. Global average pooling means we average the token embeddings across the whole review. This gives us a bag of embeddings view of the document. It is fast and surprisingly strong, but it also means word order is treated only very crudely. This code constructs the model step by step. The input is a string review. The vectorizer turns it into 200 token IDs. The embedding layer gives each token a 64-dimensional dense vector. Global average pooling compresses the whole sequence into one 64-dimensional summary. A hidden dense layer with ReLU learns a better combination of features, and the final sigmoid outputs the probability of positive sentiment. The model summary shows about 1.28 million trainable parameters. Most of the apparent complexity comes from the embedding table, not from the classifier head. The model is then compiled with the atom optimizer, binary cross-entropy loss, and accuracy as a metric. This section emphasizes a point students often miss. The embedding vectors are not fixed pre-processing artifacts. They are trainable parameters, just like the dense layer weights. During training, the model predicts probabilities. The loss quantifies how wrong those predictions are, and the optimizer updates all trainable parameters to reduce the loss. So the network learns both how words should be represented and how those representations should be combined for the final decision. This code quantifies model capacity. We have 3,500 training examples, but about 1,284,000 trainable parameters. Roughly 1,280,000 of those come from the embedding table alone, which is about 99.7% of the whole model. That is a useful warning sign. Most of the capacity sits in word representations, so if the dataset is not large enough, the model can memorize rather than generalize. For binary classification, the standard loss is binary cross-entropy. Intuitively, it rewards the model when predicted probabilities line up with the true label and punishes it heavily when the model is confidently wrong. That last part is crucial. If a system is 99% confident and still wrong, we want the penalty to be much larger than for a hesitant mistake. In marketing applications such as triage or moderation, confident mistakes can be operationally expensive. This cell gives a small numerical demonstration. The code feeds several predicted probabilities into the binary cross-entropy function. The printed averages happen to be the same for the all positive and all negative cases because the chosen probability list is roughly symmetric. Do not let that distract you. The real point is that binary cross-entropy is averaging over the whole set, and the largest penalties come from confident errors such as predicting near 0 for a truly positive example, or near 1 for a truly negative example. Once we know what loss to minimize, we need a rule for updating parameters. That is the optimizer. One of the most important settings is the learning rate, which controls step size. If the learning rate is too small, training crawls. If it is too large, the model can overshoot good solutions or become unstable. We use a toy example next because it makes this intuition visible without requiring calculus. The code minimizes a simple quadratic curve and compares several learning rates. With a learning rate of 0.01, progress is too slow, and the final solution is still far from the optimum. With 0.1, optimization gets much closer. In this toy problem, 0.8 gets closest fastest because the curve is smooth and easy. The plot shows loss falling as we update the parameter. In real neural networks, a very large learning rate can cause instability, but the toy example still teaches the main idea that step size shapes the entire training dynamic. This cell summarizes the workflow we are about to run. A batch is a small subset of training examples used for one update. An epoch is one full pass through the training data. For each batch, the model predicts, computes loss, computes gradients, and updates parameters. After each epoch, we check validation performance. That validation signal is what tells us whether the model is learning patterns that generalize or merely memorizing the training set. Now we train for 6 epochs with batch size 64. The training log shows steady progress. Training accuracy rises from about 0.56 in the first epoch to about 0.89 by epoch 6. Validation accuracy improves from about 0.59 to about 0.81, while validation loss falls from 0.66 to 0.40. That tells us the model is learning meaningful structure from the text. At the same time, training performance is improving faster than validation performance, so a generalization gap is starting to appear. The plotted curves make the same story easier to say. Training loss drops smoothly across epochs, and validation loss also drops, which is good. Training accuracy climbs steadily, while validation accuracy improves strongly at first and then starts to level off. The widening gap between the blue and orange lines is the early sign of overfitting. The model is still improving on validation by epoch 6, but the curves already hint that training much longer without safeguards may hurt generalization. This cell reminds us of the right evaluation question. Even if a deep model looks impressive during training, the important question is whether it beats a simpler alternative on unseen data in a way that matters for the business objective. Complexity only earns its keep when it delivers meaningful lift. Here is one of the most instructive results in the notebook. On the test set, the deep model reaches accuracy of 0.812, F1 of 0.834, and area under the curve of 0.931. The baseline does better, with accuracy of 0.885, F1 of 0.887, and area under the curve of 0.948. So on this task, with this amount of data and this simple architecture, the classical baseline wins. That is not a failure of deep learning. It is a reminder that strong baselines matter. The classification report gives us more detail. The deep model has very high recall for positive reviews at 0.95, but much lower recall for negative reviews at 0.68. In plain language, it leans toward calling reviews positive. That might be acceptable in some settings, but it would be risky if the business goal is to catch negative service experiences reliably. Now we shift from performance comparison to diagnosis. Overfitting means the model keeps improving on the training data, but stops improving on data it has not seen. Text models can overfit quickly because vocabularies are large, embeddings create many parameters, and labels can be noisy. A model may latch onto accidental cues, such as rare names, locations, or product terms that happen to correlate with a class in the training sample, but do not generalize. To make overfitting easy to observe, the notebook intentionally shrinks the training set to 800 reviews, with 400 per class. This is a teaching trick. By giving a large model much less data, we make memorization more likely, so the gap between training and validation behavior becomes much more visible. This code builds a much larger model with 128-dimensional embeddings, 2 dense hidden layers of size 256, and no regularization. Then it trains for 25 epochs on the tiny dataset. The learning curves show classic overfitting. Training loss falls very low, and training accuracy climbs above 0.95. but validation loss becomes unstable and often rises, while validation accuracy jumps around in the mid 0.6 to mid 0.7 range. The model has enough capacity to memorize the small training set, but not enough discipline to generalize well. This short interpretation says exactly what we should learn from the curves. If validation loss rises while training loss keeps falling, more training is not the solution. The model needs regularization, earlier stopping, or both. In other words, we need guardrails, not blind persistence. Regularization means techniques that make memorization harder and generalization easier. Dropout randomly turns off a fraction of hidden units during training, which prevents the network from depending too heavily on any single pathway. L2. Regularization adds a penalty for very large weights, nudging the model towards simpler solutions. Early stopping watches, validation loss, and stops training once progress stalls. Together, these tools help us keep useful learning while cutting back on overfitting. This cell applies all three tools. The embedding layer and dense layer receive L2 regularization. Dropout is set to 0.5, so half the units are randomly dropped during training. Early stopping monitors validation loss with patience of 3 epochs and restores the best weights instead of keeping the final ones. The model is allowed up to 50 epochs, but actually stops after 19. The curves are much healthier than before. Training improves more slowly, which is expected, but validation loss declines more smoothly, and validation accuracy rises to about 0.81. This is the right lesson. Regularization does not try to maximize training accuracy. It tries to maximize future performance. This exercise is worth pausing on in class. This exercise shows why regularization matters. First, if we lower dropout to 0.2, overfitting usually gets worse. The model can memorize the training data more easily, so training performance may improve, but validation performance often gets worse. Second, if we remove L2 regularization by setting it to 0, overfitting also usually gets worse. Without that penalty, the model can rely too much on large weights and fit noise in the training data. Third, if we increase patience to 8, the model may train too long. That can hurt generalization because the model keeps learning the training data even after validation performance stops improving. The main lesson is simple. We do not want the highest possible training accuracy. We want strong performance on future, unseen customer text. In marketing analytics, generalization is more important than memorization. Earlier in the course, Word2Vec gave us general-purpose semantic neighborhoods based on co-occurrence. In a supervised, deep model, embeddings are learned end-to-end for the task we care about. End-to-end means the embedding vectors are updated directly by the sentiment objective, not learned separately and frozen. As a result, words that behave similarly for sentiment can move closer together, even if their broader meanings are not identical. That is powerful, but it also means the embedding space reflects the dataset and the label definition, not universal truth. This code pulls the learned embedding table out of the trained model. The matrix has shape 20,000 by 64, which means each token in the vocabulary has its own 64-dimensional vector. The cell also builds token to ID and ID to token maps so we can move back and forth between words and rows in the matrix. This is the foundation for inspecting what the model learned about word similarity. Now we inspect the learned space using cosine similarity, which compares vector direction rather than raw length. High cosine similarity means two tokens point in a similar direction in the embedding space. The results are intuitive and also revealing. Great is near delicious. Love, perfect, and amazing. Terrible is near worst. Horrible, bland, rude, and awful. Rude is close to weighted and money, which hints at a task-shaped space where bad service and wasted money often co-appear in negative reviews. This is exactly what task-specific learning looks like. The model is not building a dictionary. It is shaping the space around sentiment prediction. This section introduces a tiny two-dimensional visualization using principal component analysis, or PCA. PCA is a dimensionality reduction method that takes many dimensions and finds a smaller set of directions that capture as much variation as possible. The connection to perceptual maps should feel familiar. We are again taking high-dimensional vectors and projecting them into a visual space so we can build intuition. The code selects a small set of positive, negative, and food or service-related words, then projects their embeddings down to 2 dimensions with principal component analysis. In the plot, positive words such as great, awesome, best, and love appear loosely together, while words such as terrible, rude, worst, and bad fall on another side. Tokens such as weight and dirty occupy positions that reflect service or hygiene complaints. This is not a formal market map, but it is a useful visual reminder that the model has learned a structured task-specific geometry. This caution matters. A 2-dimensional projection always distorts the original high-dimensional space, and these embeddings were trained for one dataset and one prediction objective. So we should not overclaim. The value of the plot is intuition, not proof. It helps us feel what end-to-end learned similarity looks like, while reminding us to stay modest in our interpretation. The simple pooling model averages embeddings, so it treats the document a bit like a bag of learned word vectors. That means local word order can be weakened. Phrases such as not good, hardly recommend, or never again depend heavily on order and context. Earlier in the course, Bigram's helped with some of this. A convolutional neural network, or CNN, can learn local phrase detectors directly from the sequence. Transformers push this further by letting each token attend to other relevant tokens across the sequence, not just nearby words. This optional model adds a one-dimensional convolution layer. A convolution filter slides across the token sequence and learns local patterns, much like a trainable n-gram detector. Global max pooling then keeps the strongest detected signals. The training results are interesting. Validation accuracy rises from about 0.69 in the first epoch to about 0.86 by the third epoch, then slips slightly while training accuracy races toward 1.0. So, the CNN seems to capture useful order information and outperforms the simple pooling model on validation, but it also begins to overfit quickly. This is encouraging, yet we would still need a clean test set comparison before declaring it better than the earlier baseline. This practice prompt asks what happens when we widen the convolution kernel or increase the number of filters. The business angle is important. More filters and wider kernels may capture richer patterns, but they also increase compute cost and often overfit faster. Model choice is never only about raw accuracy. It is also about latency, stability, and deployment constraints. Usually, the smaller CNN trains faster. A larger kernel makes training somewhat slower, and increasing filters from 64 to 256 usually makes it much slower. The 256 filter model also tends to overfit more quickly because it has much more capacity. In business, we should not choose the biggest model just because it is more powerful. We should choose the model that gives the best balance of accuracy, speed, stability, and deployment cost. This checklist is one of the most practical parts of the notebook. Start with data readiness. Do you have enough labels, a stable target, and a process to handle domain shift? Then ask about task complexity. Deep learning tends to help more when word order matters, when the label depends on subtle language cues, or when you need richer outputs such as multi-label predictions. Finally, consider business constraints. What is the cost of an error? Do you need low latency? Do stakeholders need interpretability? A good default rule is to build a strong baseline first, inspect the remaining error patterns, and only move to deeper models when they plausibly solve the errors that matter for the key performance indicator. I would use this cell as a discussion pause. A weekly brand sentiment monitor with a tight budget often favors a stable baseline first. Customer support triage with expensive routing mistakes may justify deeper models if the added accuracy is real. Open-ended survey coding for rare but critical complaints may also benefit from richer models if recall matters. On the other hand, a real-time ad safety filter running on device pushes us back toward lighter models because latency and compute are hard constraints. This cell should make next week feel less intimidating. The good news is that the workflow stays the same. We still tokenize text, map tokens to embeddings, train with a loss and optimizer, monitor validation, regularize, and evaluate carefully. What changes is the representation and the architecture. Transformers use subword tokenization, which breaks rare words into smaller pieces. Their embeddings are contextual, meaning the same word can get different vectors in different sentences. and self-attention lets the model mix information across the whole sequence. Fine-tuning. BERT is therefore not a brand new universe. It is the same workflow with a more powerful backbone. Let me close with the main takeaways. Logistic regression is already a very small neural network. Deep learning becomes useful when learned representations solve errors that simpler models miss. The central workflow is loss, optimizer, and validation monitoring. Overfitting is common in text, so dropout, L2 regularization, and early stopping are essential tools. End-to-end embeddings are powerful because they adapt to the task, but that also makes them task-specific. Finally, keep the business checklist in mind. Better technology is only better when it improves the decision you care about. Thank you for watching this video. See you in the next class.